Let's completely hack the Cambridge IT 9626 syllabus. Today, we are mastering control technologies to guarantee you pick up maximum marks in your exams, and we're jumping straight in with a high-stakes challenge.
We've got two different student answers for a classic 6-mark question on computerized weather stations. One of these loses easy marks, while the other is an absolute top-grade winner, and I want you to predict which is which right now.
Okay, let's hear them. Answer A says, the computer uses sensors to collect data and prints a graph. Pretty straightforward, right? But then answer B argues, sensors read analog data, and ADC converts it to digital, the microprocessor compares it to preset values, and outputs a response. So which one takes the prize? Well, we're going to reveal the winner in just a bit. But to truly understand why ordinary revision fails here, we first need to build up our technical toolkit. So the absolutely crucial point here is the difference between monitoring and control. And honestly, this trips up so many students. A monitoring system, it just gathers data. It takes zero physical action. But a control system uses real-time processing, where the output actually affects the input. The system physically changes its environment, which in turn changes the very next input reading. It's a massive difference.
To make those physical changes happen, we need actuators. So while sensors are out there quietly gathering data, actuators are the muscles of the operation. They carry out the physical action. Basically, an actuator is an output device that takes an electrical signal straight from a microprocessor and literally turns it into physical movement.
Take a linear solenoid actuator, for example. It uses a magnetic field, specifically an electrical coil wound around a cylindrical tube, to pull or push a plunger in a perfectly straight line. You'd use this exact type of actuator to automatically open sliding doors, flip electrical switches, or open up valves in a complex control system. Now, if you need some serious heavy lifting, a hydraulic actuator is what you want. It uses fluid pressure to push a piston forward. So liquid enters a lower chamber, the pressure builds up, and that fluid pressure is converted into sheer, raw mechanical power. Now, in just a moment, I'm going to reveal the exact examiner clue that transforms a basic 3-mark answer into a flawless 6-mark answer. But first, you need the underlying framework that makes this clue completely obvious. To totally hack the mark scheme, you absolutely must memorize this logical sequence. Step 1, input the preset values. Step 2, a sensor gathers the analog data. Step 3, an ADC converts that into digital data. Step 4, the microprocessor compares the reading to the preset. Step 5, the actuator receives a signal based on that comparison. And crucially, Step 6, this entire continuous loop repeats itself. Let's apply this framework to a classic exam scenario, like a computer-controlled greenhouse. If the temperature sensor's reading comes in higher than the preset value, the microprocessor signals a motor actuator to physically crank open the window. Or, if the soil moisture sensor detects that things are getting way too dry, it signals an actuator to pop open a sprinkler valve. Think about the continuous algorithmic loop required for something like a central heating system. It is constantly comparing temperatures against presets. It endlessly loops, checking if the temperature is less than the preset, signaling valves and pumps to turn on or off, and just repeating that process for as long as the system is switched on. Let's escalate things to a slightly harder example with smart motorways, where active traffic management techniques are in play. Here, computers are monitoring congestion and actually physically altering the traffic flow. The system can lower speed limits to reduce the chance of jams, or it can physically open up the hard shoulder to traffic by removing the red cross displayed on the overhead gantry. To actually collect this traffic data in the first place, systems use induction loops buried just below the road surface. These detect changes in the magnetic field from the metal in passing cars. The catch? They're really susceptible to pothole damage. Alternatively, they can use side-fire radar. This is fired at an angle to the roadside and measures speed via radar frequency changes. And the best part is, it's completely immune to road damage. Those induction loops we just mentioned? They're also the secret behind everyday car park barriers. The metal of your car triggers a change in inductance. The ADC digitizes this, the microprocessor detects the change, and then sends a signal to the motor actuator to lift the arm. A light sensor then takes over to ensure the barrier stays up until your vehicle entirely clears the beam. Traffic lights use these exact same loops to count vehicles. Think about it. If one road is totally empty and the intersecting road is backed up, the microprocessor dynamically changes the green light sequence. This continuous real-time processing is just far superior to those old fixed-time mechanical lights that keep you sitting at a red light when literally no one else is around. Moving indoors, when we network all these sensors and actuators wirelessly in a house, we get a WSAN, or a wireless sensor and actuator network. This is the whole foundation of the modern smart home and the Internet of Things. It's what allows you to remotely switch on your oven or kick on the central heating from your smartphone while you're still sitting at the office.
Now, for Cambridge Evaluate questions, you always have to balance both sides. On one hand, control systems are incredibly accurate and continuous. I mean, they never forget to take a reading. But on the flip side, they are expensive to set up, they're highly vulnerable to network hackers in a smart home setting, and the entire system fails instantly during a power outage if you don't have a reliable backup supply.
All right, let's jump back to our interactive viewer challenge and see how our newly built framework applies to those 2 student answers from the very start of this explainer. Who actually won the full 6 marks?
Well, answer A is deeply flawed. Why? Because it stopped at data collection. It completely ignored the ADC conversion and the microprocessor logic, meaning it described a monitoring system rather than a control system. Answer B, however, scores full marks. It nailed the exact continuous processing loop, including that all-important analog-to-digital conversion. To guarantee those top-band grades for yourself, you should always use the point evidence explanation framework to structure your logic. Make your point by identifying the sensor. Provide evidence by stating the ADC converts the data for the microprocessor. And give your explanation by stating exactly how the microprocessor compares this against a preset value to trigger an actuator. There is a specific quote pulled directly from the syllabus material, and it's the golden rule you absolutely must remember to satisfy the examiner. Quote, "Unlike in monitoring systems, in control systems the output affects the input." End quote. It is a continuous dynamic loop, period. So you now have the ultimate high-mark strategy for control technologies. But here is the thing. Knowing the perfect answer doesn't actually matter if you make the most common examiner report mistake. It's a fatal error that still costs students an entire grade boundary. To unlock the solution to that fatal mistake, you must watch our next explainer. So subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. And I'll leave you with this final thought. As our control systems and WSANs become infinitely more complex, if an actuator fails and randomly opens your front door in the middle of the night, who is really in control? Keep studying smartly, and I'll catch you in the next one.